right, second day with working with derivatives by definition and values of derivatives by definition. I had a second worksheet that covered those ideas. Any questions you have on dealing with definitions and working through the derivatives by definition? Once again, you can utilize either one. Limit as h approaches 0 of f of x plus h minus f of x all over h. You can utilize that one, or you can use limit as t is approaching x of f of t minus f of x over t minus x. Either one is acceptable. Either one will get you where you need to go. The first one deals with more of expansions of polynomials and binomials. The second one is more factoring of the binomials. So it's, you know, you have 6 in one, half dozen in the other. You figure out what works for you and utilize what works for you. Obviously, as we talked about yesterday, limit or the e to the x, that cannot be used. You cannot use limit as t is approaching x f of t minus f of x. You have to go the alternate definition of h is approaches 0, and we will have our trig function sine and cosine. We will have to go that direction also with respect to sine and cosine in your trigonometric functions. But anyways, questions about definitions, derivatives by definitions. It also is a very good exercise when dealing with definitions, derivatives by definitions, of utilizing your algebraic skills to be able to simplify. Because when you start getting into rational expressions, you're using a lot of your algebraic skills. You talk about your radicals, algebraic skills, and even the polynomials, dealing with working through the polynomials. You have to do binomial expansions or have to deal with some factorings there. So it's a good exercise in regards to dealing with just reviewing some of your algebraic skills. And as I talked about when you talked about calculus, that takes basically everything that you have dealt with, in mathematics throughout your career, and bringing it back in together and working through derivatives. But working through derivatives by definition is very cumbersome and very involved, and there's a lot of room for little mistakes. So as you work through equations of tangent or equations of lines and graphing equation lines, if you go back to that idea, how you graphed equations of lines to begin with, you plugged in the value of x, you saw for y, you got ordered pairs, and you plotted the points, and then you drew your line. But eventually you learned how to turn into an equation into y equals mx plus b. You found the slope and you found the y-intercept. You found it a little bit easier to be able to get through graphing equations of lines. Well, there's a lot of techniques in mathematics that are there. You have your basic definition, fundamental definition, that you can always revert back to. But there's always ways of being able to maybe just make life a little bit easier on ourselves, because we're human. We always want to make life a little bit easier on ourselves. So let's take a look at some tendencies of what happens with respect to derivatives. If I look at a function f of x is equal to x, and you want to find the derivative, the general derivative, okay, go ahead and find your general derivative of f of x equals to x. So you can use, once again, the limit as t is approaching x, or you can use the limit as h approaches 0. I will probably utilize the t is approaching, or x, or t is approaching x as I go through this. So we go f of t. Well, my function of t is just a minus f of x, which is x, over t minus x. So your limit comes down to what? What happens to the t minus x's? What can we do with them? Cancel them. Leaving us with 1 and 1. So my derivative is a value of 1. So if I have a function f of x is equal to x, my derivative of f of x equal to x is a value of 1. Well, let's look at the limit as, or let's look at x squared. So if we look at x squared, so you have a limit as t is approaching x, f of t minus f of x over t minus x. What would be your limit of x squared, or your derivative of x squared? Check your edge with somebody around you. You got the back of your top. On top you have t squared minus x squared. What would that factor to? Difference of perfect squares. Once again, it is, as you go through the ideas of limits and derivatives, it taxes you on your algebraic skills. Once again, you're going to also always get a discontinuity to t minus x that you're going to be able to remove. So the t minus x's, they moved to Texas. Leaving us with what is the derivative, Brady?
2x.
2x. We have x plus x, which is 2x. So if I have the derivative of x squared, the derivative of x squared will be the value of 2x. So if we go down to the next one, x cubed, now this taxes us even more, because if I go into x cubed, we have the limit as t is approaching x of t cubed minus x cubed over t minus x. Now, we have to remember how to factor the difference of perfect cubes, which is once again a challenge to us in the algebraic skills. Anybody remember the factoring of the difference of perfect cubes? Well, what does one of the factors have to be on top? T minus x, because we have a discontinuity we have to remove. So we have a t minus x on top. Well, if you recall back, once again, this takes us back into algebra world and a little bit into pre-calc, not much. My first multiplication is going to have to be t times something to give me t cubed. So that has to be what? T squared. So we have to have a t squared here. My x, negative x, has to go with something to get negative x cubed. So that would be what? X squared. So we have a plus x squared. So it's the first and last term. Now we have a middle term here. And remember, anybody remember how we found that middle term? Yeah, one of each, and we change the sign. So we take one of each. We have a t and an x, but we have, this is negative, this turns into a positive. And if we multiply this out, we get our t cubed. We get a negative tx squared. This gives me a positive tx squared. They cancel out. And then we have a positive x cubed, a negative x cubed. Either way, the x, t minus x's, they move to Texas. And then we can substitute in the value of x for every one of our t's. So that substitute your value of x in for your t's. So we have an x squared plus an x times x, which gives us another x squared, plus an x squared, so gives us what, Ian?
3x squared.
3x squared. X to the fourth. Now this takes us back to the difference of perfect squares. So we have the limit as t is approaching x, t to the fourth minus x to the fourth over t minus x. So we have a limit as t is approaching x. First factor of that is the difference of perfect squares. If I have x to the t to the fourth minus x to the fourth, factors the difference of perfect squares. What are you going to have to multiply to get t to the fourth? What are you going to have to multiply to get x to the fourth? Something by itself. T to the fourth minus x to the fourth?
T squared minus x squared times t squared plus x squared.
So we have t squared minus x squared and t squared plus x squared. Middle terms cancel out, which we can then factor our first term. We can factor our t squared minus x squared again as difference of perfect squares. Okay, we should still get our same canceling to t minus x's, and then substitute in your x for all your t's, and simplify that down. Check your answer with somebody around you. Once again, your t minus x's, they'll move to Texas. Substitute in x for t. X plus x with the first term. Second term is x squared plus x squared. So we have x plus x gives us 2x. We have x squared plus x squared, which is 2x squared. So if I take the derivative, what do we come down to, Alex? 4x cubed. All right, x to the 6. If we take a look at x to the 6, well, now we have difference of squares, difference of cubes that we're going to have to worry about. So I will take us through this one. Difference, it does not matter which one you deal with here. I'm going to deal with the difference of cubes first, which gives me x squared minus Oh, let's try this one more time. Take it back to the beginning. My bad. We have t to the 6 minus x to the 6 over t minus x. So the limit as t is approaching x. If we deal with this as a difference of cubes, we have t squared minus x squared. Then we have t to the 4th plus t squared x squared plus x to the 4th over t minus x. One of each. Then I have my combo here. And then we can factor again. T minus x, t plus x. Then we have t to the 4th plus t squared x squared plus x to the 4th. And that's over t minus x. Once again, this will cancel out our t minus x's. We'll move them to Texas. And then we can put all our x's in for the t's. So we have x plus x is the first one. Second one, x to the 4th plus x squared plus another x to the 4th. A lot about algebra here. First one will give us 2x. Second one will give us x to the 4th plus x to the 4th plus x to the 4th. So we would have 3x to the 4th. So we have 2x times 3x to the 4th, which gives us 6x to the 5th. All right, let's take a look at patterns here. Yes, if we wanted to, we could go x to the 8th and go hog wild on x to the 8th. But just take a look at what it's occurring here. If I have x to the 1st, my solution is just x. If I wanted to, this would be x to the 0th power. Because anything to the 0th power is 1. When I had x squared, my derivative was 2x. That would be 2x to the 1st. When I had x cubed, my derivative was 3x squared. When we had x to the 4th, my derivative was 4x cubed. When we had x to the 6th, my derivative was 6x to the 5th. So if we were taking a look at x to the 8th, following the pattern, what would be the derivative of x to the 8th? Nick?
8x to the 7th.
8x to the 7th. What is occurring here in each one of our functions that we dealt with here, my exponent came out to my coefficient. So my 6 came out to the front. My exponent of 4 came out to the front. My exponent of 3 came out to the front. My exponent of 2 came out to the front. My exponent of 1 came out to the front. Okay? And what happened to the exponent of our derivative? What do we do with our exponent, to our function, to get to our derivative? What happened to our exponent here? At 8 down to 7, 6 down to 5, what are we doing? Subtracting 1. So we are subtracting 1 from our exponent, and our coefficient is running out front. So if I bring my coefficient out front, or exponent out front, and we subtract 1, we can come up with our derivative. This is what we call an exponent. Well, what happens when we have 5x squared? What happens when we have 5x squared? Well, is the same thing going to apply because I have a coefficient now? Before I never had a coefficient. Let's see what happens. If we go back to definition, we have the limit as t is approaching x of f of t, 5x, oopsie, 5t squared minus 5x squared over t minus x. I can factor 5 out of each term on the top. So we have 5t squared minus x squared over t minus x. My t squared minus x squared, that cancels out. So we have a limit as t is approaching x of 5t minus x, t plus x over t minus x. Once again, the t minus x's, they moved to Texas. And we can substitute our x in for t. So we have 5x plus x and the key thing to look at here is I still have the x plus x, which gives me 2x. So my x squared derivative still came down to this 2x. And we can multiply by the value of 5, which is my coefficient. So we come down to 10, x is our derivative. But the key idea to think about here is my derivative of x squared. My derivative of x squared still gave me 2x. And we can take the 2 times the 5 to give me the value of 10. So if we take a look at our next derivative, 7x cubed. I want to find the derivative. Well, all we're dealing with is the derivative of x and using our exponent rule for the derivative of x cubed. Well, if I take the derivative of x cubed, what do we come up with? 3x to the second. So we have 7 times 3x squared, because my derivative of x cubed gives me 3x squared. So we have 7 times 3, which is the value of 21x squared. If we wanted to, we could still take this back to the limit as t is approaching x of 7t cubed minus 7x cubed over t minus x, and do a bunch of factorings if we wanted to. But now what we're learning is what is called an exponent rule for derivatives. You will still be responsible for on your test taking the value or the derivative by definition on a couple problems. But what we also can do is we can start taking a look at derivatives by using our exponent rule. When dealing with the exponent rule, if I have a function in the form of ax to the nth power, a times x to the nth power, and we want to find the derivative of ax to the nth power, we could take our exponent, move it out front, multiply our coefficient by our exponent, and then subtract 1 from our exponent. And this would be our exponent rule for derivatives. The key, though, is you need to be able to get it in this form right here. I need to have a coefficient times a variable to an exponent. It has to be multiplication. It cannot be division. It has to be multiplication. The other thing to take a look at is if we take the derivative of a constant. Okay, let's take a look at the derivative of a constant. F of x is equal to 13. A constant. Well, if I take the limit as t is approaching x of f of t, which is 13, minus f of x, which is 13, over t minus x, I get 13 minus 13, which is 0, over t minus x. 0 divided by anything is still going to give us a value of 0. Or if we look at this as an exponent rule, This would be 13 times x to the 0th power. If I have no variable there, that means I have x to the 0th power. I can multiply 13 times 0 times x to the 0 minus 1 power. Well, 13 times 0 is going to give me 0. Times this value, I'm still going to get a value 0. So whenever I take the derivative of a constant, my derivative of a constant will always equal the value of 0. Well, what happens if I have 6 square root of x? I want to find the derivative. Well, what we had up till now is the limit of t is approaching x, square root of t minus square root of x over t minus x, and we had to factor our bottom down to square root of t plus x, square root of t minus x, do some canceling. Now using the exponent rule, once again, now we're going to be taxing our algebraic skills. If we have square root of x, how can we rewrite square root of x as an exponential rule, or as an exponent?
6x to the 1/2.
6x to the 1/2. So my function turns into 6 times x to the 1/2 power. So we had to put it in the form that we can work with. Now we can use our exponent rule. So apply your exponent rule to this. Well, exponent rule, very exponent comes out front. So we have 6 times 1/2. And then we have to subtract 1. So we have 1/2 minus 1. So we have negative 1/2. Now solutions, when we deal with solutions, my rules for solutions are no negative exponents, and radicals need to be in simplified radical form. You will not have to rationalize though, but they need to be in simplified radical form. Well, 6 times 1/2, that gives me a value of 3. What's the negative exponent tell us to do? Take it to the bottom. So we have, this is 1 over x to the 1/2. And x to the 1/2 we can put back into radical form. So we have 3 over square root of x. Once again, need to eliminate negative exponents. Need to put it in simplified radical form. Do not have to worry about rationalizing now. We have enough stuff to worry about here. I'm not going to ask you to rationalize the 7th root of x to the 3rd. Well, what if we have 7x to the 4th power? Need to take this and move it into an exponential form of a times x to the nth power. Well, this is a divided by x to the nth power. We need a times x to the nth power. How can we rewrite this in the form of a times x to the nth power? How can we take the value x to the 4th out of the denominator and move it into the numerator? And
Make the exponent negative.
make the exponent negative. So we have 7x to the negative 4th power. So now we can use our exponent rule. Take your exponent times your coefficient. Drop 1 from your exponent. Then put it in an acceptable form, which just means eliminate your negative exponents and check your answer with somebody around you.
Not negative.
No, what did he come up with?
Negative 28 over x to the 5th.
That is correct. My derivative, we have 7 times negative 4, x to the negative 4 minus 1 power. So we have negative 28, x to the negative fifth power, and the x to the fifth power will drop to the bottom. So we have negative 28 over x to the fifth. Which now leads us into this problem, a typical problem we've done already. I want to find the equation of the tangent line of this function at x equals 4. Well, what we have done up till now is we found the slope of the tangent line by dealing with the value of our derivative at a value of a, which is the limit as x approaches a of f of x minus f at a over x minus a. Okay, that's what we've gone through before. But the key thing to remember here is our slope is the value of the derivative at a, at 4. We can run it through this if we want to. But what we can now do is we can define all of our slopes by looking at the derivative of our function. Well, now we have a derivative of polynomial. We can take the limit as x approaches a of each term of the polynomial, or we can use our exponent term, our exponent rule, for each term of the polynomial. If you take the derivative of 4x cubed, the derivative of 4x cubed will give us what, Jamie? 12x squared. We could take the derivative of negative 5x squared. Then take the derivative of negative 7x, then take the derivative of 5. Take the derivative of each individual term. Rather than running it through the limit as x approaches a of f of x minus f of a over x minus a and having to factor all that stuff down, we can now just take our derivative. What would be the rest of our derivative here?
Minus 10x minus 7.
Okay?
0.
Well, 0, because I take the derivative of the constant, that goes bye-bye. Well, this gives me my value of my derivative, or my function of my derivative. So to find my slope, I can find the value of my derivative at the value of 4. Our slope comes down to what? Tristan, what's it come down to?
The 145.
I'm sorry, what?
145.
145? That's our slope? Oh, my bad. I forgot we squared 14, or 4 there. I was taking 4 times 12, 48, minus 40, minus 7. I thought we had a 1 there. I forgot we had that. And then we can find our point of tangency. Our x value is 4. We can find our function value at 4 to find our point of tangency. Our y value is what, Galen? 153.
153.
And then we can find our equation, 145, x minus 4 is equal to y minus 153. But the key thing to remember here now is the slope is the value of our derivative. So we can find our derivative, and then find our slope, rather than taking through the limits as x approaches a. Life, just a tad bit easier with derivatives. We also have product rules. We have two other rules to go through. The product rule. If we have two functions that are being multiplied together, we have what is called, since they're being multiplied, the answer to a multiplication problem is a product. Two things that are being multiplied together gives us a product. We can find the derivative of these two terms, or of this function, is the derivative of our first term times our second, plus our first term times the derivative of the second term. When functions are being combined together through multiplication or division, we cannot deal with the derivatives together all at one time. We can't do it in one fell swoop. We have to take the derivative of each individual term and multiply by the second term, by the third term, or whatever. We can't take the derivatives of both of them together. So if we look at h of x is equal to 5x squared plus 4 times 7x cubed minus 3. If we wanted to, we could FOIL this out. But what happens if you have two trinomials or two four-term polynomials there? And multiplying that out, yes, you can do it, but it's going to be very cumbersome. We can utilize the product rule to be able to find our derivative, which is the derivative of our first term, 5x squared plus 4. So take the derivative of that first term, 5x squared plus 4, and multiply it by the second term, which is 7x cubed minus 3. You don't do anything with the second term, you just leave it alone. Derivative of 5x squared plus 4 is what, Phoebe? 10x. So we have 10x times our second term, 7x cubed minus 3, plus the first term, which is 5x squared plus 4, times the derivative of our second term. Derivative of 7x cubed minus 3 is what, Alex? Yeah.
70x. Oh wait.
Use your calculator.
Sorry, 21x squared.
21x squared. Now, if you wanted to, you could FOIL this out and combine the like terms. A lot of times, you're not going to have that capability. I'm fine leaving it in that form there. We also have the quotient rule, two things being divided by. One function divided by a second function. We could take the derivative of, using our quotient rule, as very similar to what we did with the product rule. The derivative of the top, f prime at x, the derivative of the top, times the bottom. The derivative of the top times the bottom. And the second one is the top times the derivative of the bottom. Same thing we had with the product rule. But the difference with this is we throw a subtraction in there. This turns into a subtraction. And then what we have to do with our denominator is square our denominator. We will work on this more tomorrow, Wednesday, or Thursday, Friday. We'll be dealing with derivatives a lot and the rules of derivatives. But what you'll should see is life is a little bit easier. Solutions are posted on Classroom. Adios. Have a good day.